Hi everyone, welcome back. Up until now, we've been finding the pH of acidic solutions, but we can also find the pH of basic solutions as well. Now let's remember that a strong base completely ionizes in solution. And here's a table of the strong bases we are covering in my course. Now make note that there are other strong bases out there as well that you would learn if you went on to take organic chemistry. But for now, you only need to worry about lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, and barium hydroxide. Essentially, they are group 1A and group 2A hydroxides that are strong. For example, if we have sodium hydroxide, it dissociates into the sodium cation and the hydroxide anion. So if you wanted to calculate the pH of the solution, since sodium hydroxide and the hydroxide are in a 1-to-1 ratio, then the concentration of sodium hydroxide is equal to the concentration of the hydroxide ions. Also recall that pOH is equal to the negative log of the hydroxide ion concentration, and that pH plus pOH is equal to 14. And so from here, if you have the hydroxide ion concentration, you can find pOH, and then from there, you can find the pH of the solution. Now, if you had strontium hydroxide as your strong base, then that breaks up into the strontium cation plus 2 hydroxides. And so the mole-to-mole ratio is a little bit different there. The hydroxide ion concentration would be equal to 2 times the strontium hydroxide concentration. So for example, if you had a 0.1 molar solution of sodium hydroxide, the hydroxide ion concentration would be 0.2 molar. But once again, once you figure that out, you'd find the pOH, and then you could find the pH of the solution. Now with weak bases, they partially ionize. And as we see here, ammonia and its derivatives is like the classic example of a weak base. We can see in our beaker that we have several of the ammonia still intact and just a little bit of dissociation taking place in the form of ammonium cation and the hydroxide anion. Now here's a table of some weak bases. It's not a comprehensive list, but it gives you an idea of some common ones we may run into, like the carbonate ion, methylamine, ethylamine, ammonia, bicarbonate, pyridine, and aniline. It also gives you the ionization reactions. You can see they have the production of the hydroxide as a very common product here, and then it gives you the list of the Kb values. So let's talk about that. What is the general form of this ionization reaction? I'm going to represent base B in the presence of water. So this is my base, therefore water must act as an acid. Remember, a base is a proton acceptor, and my acid is a proton donor. All right, so that will help me to predict the products. We're talking about a weak base. We're using equilibria arrows here. If my base is accepting a proton, it turns into HB. Originally in this equation here, it was neutral. So now it turns into positive, and that is the conjugate acid of my base. And the conjugate base of the water, which is acting as an acid, donated a proton. So it lost a proton here. It turns into hydroxide. So that's the conjugate base, as we see here. So something just to make note of when it comes to charges. Remember, these acid-base reactions are just a transfer of one proton at a time, and so therefore it's only a positive charge. So I'm giving you an example of a base that's neutral because I was basing it off of ammonia. And so when it gains a proton, it turns into this positive conjugate acid. You can see the same thing for ethylamine, methylamine, for pyridine, and for aniline. However, when you do something like bicarbonate and it accepts a proton, bicarbonate was already negative. So when it accepted a positive, its conjugate acid was neutral. But once again, you still get the conjugate base of water as the other product. So just be mindful of your charges, that you're adding a positive charge. So for example, carbonate, -2 + 1 equals a -1. So just keep track of that as you're predicting the products for your weak acid and weak base equations. All right, so let's continue on. Let's talk about Kb. So Kb is the equilibrium constant for a weak base. Still products over reactants. So in this case, it's the conjugate acid of the base times the concentration of the hydroxide, which is the conjugate base of water, over the concentration of the base. Now the trend for Kb is the same as it is for Ka. If Kb is a lot less than 1, then we're looking at a weak base. And if Kb is greater than 1, then we're looking at a strong base. Just like with Ka, generally with acids, we look at the pKa. We do the same for bases. We look at the pKb. And the pKb is equal to the negative log of the Kb. Remember that little p is just a mathematical operator to represent negative log. And helps us to work on a scale. It's a little bit easier to understand and remember. The trends for pKb: the smaller the pKb, the stronger the base. So once again, just like with pKa, the smaller the pKa, the stronger the acid. The smaller the pKb, the stronger the base. So there's a lot of similarities between the two. And that's why it's really important for you to identify, are you working with a base? Are you working with an acid? What's in your beaker? All right. Now something I want to make note of, it turns out that many weak acids have a nitrogen atom with a lone pair that acts as a proton acceptor. So you can see here in these diagrams, this is ammonia, you see the lone pair. Methylamine is a nitrogen with a lone pair, and pyridine. They're actually pretty good weak bases, not strong bases, but they're weak bases. And I wanted to show you what happens here. So if you have ammonia, and water, then these electrons here come in and pull off the proton off of water, because ammonia is the base, it's a proton acceptor. And these two electrons that were shared between oxygen and hydrogen in water go on to the oxygen atom. So then you get ammonia now has an extra hydrogen here, that proton from water. And that means that nitrogen has a +1 formal charge. That's the ammonium cation that's produced. And then water lost a proton, but those 2 electrons that were connected between the oxygen and hydrogen in that shared bond now turn into a lone pair. And now this oxygen has a -1 formal charge, and you know it to be the hydroxide anion. So I wanted to show you this mechanism and the electron flow so that you can understand how the lone pairs serve a purpose as pretty decent bases. So if you have a lone pair on a nitrogen, it likes to pull off hydrogens off of any acidic source, so in this case water, and it accepts it, forms that new bond, and now we have the conjugate acid of that nitrogen or the ammonia derivative, and then the conjugate base here of water, which is hydroxide. And so you could show similar examples of methylamine and pyridine in water as well, acting as weak bases. Let's do an example together. Amphetamine is a weak base with a pKb of 4.2. Calculate the pH of a solution containing an amphetamine concentration of 225 milligrams per liter. So we're identifying from the context of this problem that we have a weak base. Another clue is the fact that there's a nitrogen. We also are given the pKb is 4.2. We want to find the pH of the solution, and we're given the initial concentration in milligrams per liter. So first things first, I know eventually I'm going to have to do a rice table and set up a Kb expression. So I'm going to figure that out first. I'm going to write up here actually because I know that we need lots of space here. So pKb is equal to 4.2. To find the Kb, that's 10 to the negative pKb, so 10 to the negative 4.2, so that's 6.309573 times 10 to the negative fifth is the Kb, so we'll use that in a little bit. In addition, when we do a rice table, for Kb, we work in concentration units of molarity. So I'm going to convert the 225 milligrams per liter into molarity, moles per liter. So there are 1,000 milligrams in 1 gram, and then I'm going to convert the grams into moles using the molar mass of amphetamine. So we have 1.66412 times 10 to the negative third molar. All right, so let's go ahead and set up our rice table here. We got to figure out the reaction first. So we have C9H13 in the presence of water. Water is going to act as an acid here since we know amphetamine's a base. It's a proton acceptor. And so now that you understand that the nitrogen is what's taking off the proton, I will write the formula of the conjugate acid more like an organic chemist, where we're trying to elucidate the actual correct atom-to-atom attachments. A lot of times you'll see some chemists put the hydrogen just out in the front, like you would for any acid. You put the proton in the front, but I just wanted to be true to form here. I would accept either way since this is a second semester general chemistry course. So what I mean here is that I know my amphetamine is gaining a proton. I'm actually writing that proton here at the end of the formula because I know it's attached to this nitrogen. Some chemists would write it at the beginning because that's how a lot of acids are drawn in general chemistry or inorganic chemistry. But I'm attaching it to that nitrogen there. And then remember the conjugate base of water, it lost a proton because it's acting as an acid, so that's why we have hydroxide as the other product there. And then initially we put in our beaker 1.66412 times 10 to the negative third molar. And then this is essentially 0. Yes, we do have some hydroxide ions in solution from the auto-ionization of water, but not a significant amount. Reactants change by decreasing over time. The products are increasing. Everything's a 1-to-1 ratio. So that's why it's minus 1x plus 1x plus 1x. And then 1.66412 times 10 to the negative third minus, and then I'm just going to say minus x here, at equilibrium. 0 plus 1x is x, and then same for the hydroxide. So in the end, I know eventually I need to figure out the pOH to figure out the pH, and from there, before I get the pOH, I need the hydroxide ion concentration, and I'm going to get that from this Rice table here at equilibrium. I just need to solve for x, right? It's the goal. Okay, to do that, I'm going to set up the Kb expression here. So Kb is products over reactants. And that's equal to x squared over the 1.66412 times 10 to the negative third minus x. And up here we solve for Kb for amphetamine. It is 6.3 times 10 to the negative fifth. Now in this case here, you could try to ignore x, but x will be too small. It will be not small enough to ignore. And so I'm going to go ahead and do the quadratic to save us some time and some space here. And so need to convert this into an ax squared plus bx plus c equals 0 format here. And so when you do that, that's x squared plus 6.31 times 10 to the negative fifth x minus 1.05 times 10 to the negative seventh is equal to 0. Make sure you feel comfortable converting this into that quadratic form of ax squared plus bx plus c is equal to 0. So a is 1, b is 6.31 times 10 to the negative fifth, c is negative 1.05 times 10 to the negative seventh. And then x is equal to negative 6.31 times 10 to the negative fifth plus or minus the square root of 6.31 times 10 to the negative fifth squared minus 4 times 1 times negative 1.05 times 10 to the negative seventh over 2 times 1. So x can either be 2.94019 times 10 to the negative fourth, or x is equal to negative 3.5711 times 10 to the negative fourth. Now, which one of these solutions is not going to work out? This one here, right? Because it would give you a negative concentration, and that is not going to happen. So we're definitely not going to use this. So therefore, x is equal to 2.94 times 10 to the negative fourth. That is our hydroxide ion concentration at equilibrium. So hydroxide ion concentration at equilibrium is equal to 2.94019 times 10 to the negative fourth molar. the pOH is equal to the negative log of that concentration, which would be 3.53, and then the pH is equal to 14 minus the pOH, which is 10.47. Always ask yourself, does this make sense? What is in my beaker? It's a weak base. Therefore, you would expect this solution to be greater than 7, the pH to be greater than 7, and basic. All right, so make sure you review over this information, understand how to predict the products of a weak base equilibrium, to set up the Kb expression here, to understand that if you are working with a weak base, that this is not a hydronium ion as the product, but rather the hydroxide. And once you solve for X, that's that concentration of the hydroxide, which you will use to solve for the pOH of the solution. And then from the pOH, you can find the pH. Thank you all for watching, and I'll see you next time.